Homework 7b. Question number 1. Calculate the standard Gibbs energy and equilibrium constant at 25 degree, 50 degree for the following reaction. Note that we have formation Gibbs energy for reactants product, formation enthalpy for the reactants and the products at 25 degree, and therefore we can calculate the reaction Gibbs energy at 25 degree. So formation Gibbs energy of product minus reactants. So this is the reaction Gibbs energy at 25 degree. Now we use this equation, all right, standard reaction Gibbs energy, which is calculated. We can calculate a K constant. Temperature is room temperature, 25 degree. Okay, so calculate K is 1.3 times 10 to the 54 power. Okay, when you calculate, please pay attention to the unit. Delta G is in kilojoule and R is in joule. All right, so you need to times 10 to the third power. Okay, so that's 25 degree. How do you calculate the 50 degree K? Now we don't have the formation. We don't have formation Gibbs energy for 50 degree, so we cannot calculate reaction Gibbs energy at 50 degree. Instead, we have to use Van Hoff equation. All right, so now we use this as K1 and 25 degree as T1 and 50 degree is T2. Okay, remember to change to Kelvin. But in the equation, we still need to calculate the delta H, reaction enthalpy. First, we need to calculate this one. This is calculated by formation enthalpy minus a product minus reactants. And note that it says it's independent of temperature. So the formation enthalpy calculated at 25 degree can be used for the 50 degree, for the whole temperature range. Okay, so we're going to do it in the next slide. So in this Van Hoff equation, we need to calculate reaction enthalpy. Okay, using the formation enthalpy product minus reactants, and the answer is negative 336.59 kilojoule per mole. Note that this is negative, means it's an exothermic reaction. Okay, and then plug into this equation. All right, we can calculate K2. K2 is in this equation, we label it as 50 degree. So at 50 degree K, this is at 25 degree K. So this is K1, this is K2. All right, and T2, T1. All right, and delta H plug in. All right, so again, pay attention to the unit. Kilojoule becomes joule times 10 to the third power. All right, so you can calculate K2, or K at 50 degree is 3.5 times 10 to the 59 power. With this K, then we can calculate delta G. Okay, delta G at 50 degree can be calculated using negative RT ln K. Okay, at 50 degree, and that gives you negative 306.52 kilojoule. Question number 2. Explain how to use the Chatelier's principle to predict the equilibrium shift with temperature for the reaction described in the last question. So remember, last question we calculated at 25 degree, K is 10 to the 54 power. But if you increase temperature to 50 degree, K becomes 10 to the 49 power. So temperature increase, equilibrium constant decrease. Okay, so it decreases equilibrium constant. So how do you use the Chatelier principle to justify this? Now, for the reaction, if we want to look at temperature dependence, we need to know whether reaction is endothermic or exothermic. And the calculated delta H tells us delta H is negative 336. A negative one means it's exothermic. So the reaction releases heat to the surrounding, and in the equation we can think about heat as a product because it releases heat for the reaction, exothermic reaction. Now if it's endothermic, then you think heat as a reactant, so you add on the left side. But here you add on the right side, okay? So that's the product. Now if you increase temperature, that means you increase heat, and heat is a product, so you add product to the system, and the system will go counteracts, which means it go to the reactants. It go reverse reaction to decrease product, all right? And that will decrease equilibrium constant because the reaction go reverse reaction, all right? Decrease K constant. Question number 3. Calculate the percent change in Kx for the following reaction when the total pressure is increased from 1 bar to 2 bar at a constant temperature. So the temperature, the pressure dependence of a chemical reaction has this equation. Kp, equilibrium constant in terms of pressure, is Kx times P to the delta V power. This is 1 bar, we don't need to look at that. And delta V is the power of the product, where you have 1 more carbon monoxide, 1 more hydrogen, so that's 2 moles in total. Reactant has 1, so delta V is 2 minus 1, give you 1. Okay, so that give you Kxp times P, and therefore we can calculate P. Kx is Kp divided by P. Okay, so Kx equals Kp divided by P. Now because we want to calculate the Kx, all right, so we want to calculate the Kx change, all right. There are several ways to do it. One way to do it is that assume when P is 1, so Kx is Kp divided by 1. But when P is 2, okay, pressure is 2, then Kx, now we write as prime, different Kx, which equals Kp. Note that Kp doesn't change. It's the Kx that may change with pressure. And so the pressure now becomes 2. And so we want to calculate the ratio, these two ratio. And therefore, here is the ratio. So Kx prime divided by Kx. So this is when pressure is 2, this is when pressure is 1, and plug in Kp, the same, cancel each other. You get 1 divided by 2. That means when pressure increases twice, the equilibrium constant in terms of mole fraction decrease by half. So Kx decrease 50%. Explain how to use the Le Chatelier principle to predict the equilibrium composition shift with pressure change in the last question. So in order to look at the temperature dependence as last question, we look at whether the reaction is endothermic, exothermic, add heat, whether to the reactants or product. Now if we look at the pressure dependence, then we look at the number of moles change and see how this number of moles change affect the pressure. So for this reaction, the reactant has 1 mole gas phase, the product has 2 moles. So if a reaction go forward, that will increase number of moles, which has an effect to increase the pressure. The reverse reaction decrease number of moles, that will decrease pressure of the system. Okay, so now if you have a disturbance, and that's pressure increase, and this is a disturbance, the system will react in a way that counteracts the disturbance, and that's the reverse reaction, because reverse reaction will decrease pressure. that counteracts the disturbance to increase pressure. All right, so when pressure increases, equilibrium will shift towards the direction to decrease number of moles. In this case is the reactance, okay, reverse reaction.